Okay, so again, I am sorry for the long interruption, and just to clarify the situation and where we are, we completed basically rainfall runoff modeling. You completed with the IMOD model, and keep in mind that the question about the IMOD model can be asked at the exam. Usually I ask the question of the IMOD model if I see that your performances are very good. To me, you see, the mathematical development is not easy, and therefore for me it's a question that I consider quite tough, but in any case it's something that I can ask. And basically the typical details that I ask, if I see that you're good, I may ask to derive through integration the expression for the storage for W. And also the typical question that I ask is how many parameters the IMOD model counts, and to describe the meaning of these parameters, things like this. Or I may ask you, for instance, what happens if the value of beta is 0 or 1 or tending to infinity. And again, these are typical questions. And so with the IMOD model, we completed the list of the rainfall runoff model that I wanted to consider. And now I'm talking today about calibration of rainfall runoff model, meaning parameter fitting. And then I will talk also about verification of the performances. And I will focus again on infiltration models, which are infiltration models are very important for us because they allow us to determine how, let's say, what is the part of rainfall that after the rain event, infiltrates into the soil. And therefore infiltration models are a kind of detail over rainfall runoff models. I will explain also how infiltration models can be included in rainfall runoff models. And then after infiltration I will turn to another topic. No more hydrological modeling, but another topic. So this is the sketch. So today, now I would like to speak about calibration, and we have already available on the website the file on it. It was already available at the beginning of our lecture. Let me adjust the resolution of the screen and then we can start. Maybe it's also better if I turn off the light here. Okay. So let me see. Yeah, it's better if I change the resolution. Good. Perfect. Okay. So model calibration and validation. Validation is a synonym for verification. So we first speak on calibration and then validation. Again, validation is a synonym for verification. Validation is used in the Italian language. We say validazione, and this is the typical term that we use. Abroad, validation is not much used, is still used but not much, and they prefer very often to use the term verification instead of validation. Okay, so first of all, calibration. Calibration is an operation that aims to estimate the parameter values for hydrological models. And I think you already have an idea of what parameters are. For instance, if we talk about IMOD, the parameters, as you well know, are the maximum water storage in the soil, the parameter beta, the parameter alpha, which means subdivision of the runoff production in surface flow and subsurface flow, and also the two bottom discharge parameters for the two linear reservoirs. And of course, these parameters need to be assigned a value, and this is done through calibration. Just to be clear, when we refer to the linear reservoir, the parameter is just one, and it's the parameter K, the constant that regulates the outflow from the bottom discharge. And when we talk about the time area method, the parameter is 1 and it's the concentration time. And of course it needs to be estimated. So first of all, what are parameters? Parameters, I think I already defined what they are. It's difficult to find in the literature a unique definition for parameters. This is a definition that I elaborated myself, but I think it's both understandable and hopefully correct. And a parameter can be defined, if you look at the model equation, as a constant or even a variable term, where with variable I mean a term that is variable during model application, or it can be variable a long time. And this constant or variable term, which appears in the model equation, doesn't determine the general form of the equation, but determines the specific form. And let me refer to give to a very trivial example to the equation of a straight line. The equation of a straight line can be written as fx is equal to a multiplied x, where x is the independent variable and a is a parameter. So this is the equation of a straight line, and it remains a straight line whatever value a takes. But of course the slope is equal to a, so it means that the specific form, the specific appearance of the straight line is determined by a. The line remains straight, but the slope changes. So this is, I think, an easy to understand definition of parameter. So for instance, for the linear reservoir, if you change k, you don't change the general structure of the model, but you change, of course, the specific structure, and also you change the response. Okay, so this is the definition that we can accept for parameter, and let's keep into account that parameters are always present, included in hydrological models. Even if you write an hydrological model in a fully physically based form, which means that you use the relationships given by the theory of physics, then anyway you have parameters. Let's think, for instance, to flood routing. You have the de Saint-Venant equation, which are the equation that determines how water flows into a river, and they are fully physically based, but in this equation you have the roughness included, the roughness which quantifies the energy losses that are experienced by the river flow while flowing, and the roughness can be considered a parameter. It is a parameter that has a physical meaning, but still it's a parameter. This means that parameters can be, in principle, and at least some of them, can be estimated by physical reasoning. For instance, the roughness can be estimated by physical reasoning. Roughness is scabrezza in Italian, just to be clear. Because you go over a river, you look at the river, and by looking at the type of vegetation cover in the riverbed, by looking at the size of the gravel along the riverbed, or the size of the boulders if they are, by looking at these behaviors, you can get an estimate of the roughness, because roughness is indeed a physical parameter. So some parameters may in principle be estimated not through calibration, but just through physical reasoning. But usually there is to say that the term parameter is reserved for quantities that are not physically measurable. And so let me better explain, because I said that roughness is a parameter, and then I said that roughness has a physical meaning and can be guessed, but then I'm saying that parameters usually are reserved for quantities that cannot be physically measured. So there is at least an apparent contradiction here. Now, let me explain better. Roughness can be at the very end guessed, but indeed, if you roughness typically, because it's a parameter, compensates other deficiencies of the model. So if you go to calibrate roughness, very often you will see that the values taken by this parameter are not really physically meaningful. And this is why the model is not perfect. And when you calibrate the parameters, you also obtain a compensation effect. Like, of course, you try to find the best value of the parameters, and in doing so, you compensate with the parameter values other deficiencies of the model. Because the parameter is an element of flexibility. So the model has a fixed structure, but of course, by changing the parameter, you get flexibility in changing the response. So the parameter may also be used to compensate for other approximations. And this is the case of roughness. It's a very good example, because what experience tells us is that if we try to guess the roughness, usually we don't get a good model response. So basically, let me say that in order to be, I think, clearer, if you have a parameter that has a physical meaning and the value is clearly defined, and let me make the example of the gravity, I wouldn't use the term parameter. Parameter is something that can be adapted through calibration. Gravity, I think, is a good example, because indeed, in our models, it can be treated as a parameter, but you wouldn't think to give to gravity a value of, which is not the real physical value, because gravity indeed can be really measured. So nobody would use the term parameter for gravity. So the moral of the story is, the parameter is something that may change in a model. It may have some partial physical meaning, so we can get a guess of its value, but still is something that needs to be adapted. Good. Now, to complete this premise, let's not forget that this is a very useful behavior for us. The fact that parameters can be adapted, therefore obtaining a compensation for other approximations, is a very useful behavior of hydrological models. Very useful. So why this is useful? Because, as you well know, because at the beginning of these lectures of this course, I repeatedly mentioned this fact. As you know, I said, hydrological models are always uncertain. They only provide an approximation of the reality of the underlying actual processes. And therefore, you know, any hydrological model, even if it claims to be fully physically based, has actually a certain degree of conceptualization and a certain degree of uncertainty, which of course we have to minimize. So it's very useful to have this opportunity by tuning the parameters to use some flexibility to optimize model performances. This is why calibration is deemed to be a very important step for hydrological model application, because it allows us to adapt the model equation to the specific application. And therefore, calibration may seem to be a difficult term. It's nothing else than tuning. Like, you get the parameter value, and you look at the model response, you compare in some way, we will see how, the model response with the actual observation, and then you tune the parameter value in order to make the model response as close as possible to the actual observation. There are today some software that indeed allow you to tune. With the mouse, you just click over a bar and change the parameter value by looking at the response and the comparison of the response with the observation. So, and this is what is called adaptation of the model output to observed data. And it's very useful in doing so to have an initial guess. So if the parameter has some physical meaning, this initial guess that you may obtain by considering the physical meaning is very useful. Okay, that's it. And let's not forget that calibration has many synonyms, which include parameterization, optimization, parameter estimation. So just let's treat them as synonyms. In hydrology we often use calibration, but very often you will find also the use of terms like parameterization, optimization, and others. So I spoke just a couple of minutes ago of manual tuning. I said you look at the comparison between observation and model simulation and you tune the parameter value. This tuning is particularly easy if you have just one parameter, because if you have just more than one, then it becomes a little bit difficult to tune two parameters at the same time. Anyway, this type of calibration is called trial and error. So when you tune by looking at the comparison between model simulation and observation, you make a trial and error calibration. Trial and error means I try, I look at the errors, and then I make another trial. This type of calibration, as I said, is particularly appealing when you have only one parameter. If you have 5 parameters, this is very difficult to do. And let's say also that this trial and error calibration requires a certain experience by the modeler. You have to know well the model, especially if the number of parameters increases. And therefore, if you really know well the model, then you may be able to perform a good trial and error calibration. There is an alternative that is increasingly used, which is the automatic calibration. This is done through computer algorithm. And there is a very relevant research activity that has been carried out in the past 20 years on optimization of calibration algorithms. And they started about 20 years ago with this kind of activity, because about 20 years ago we had a massive expansion of personal computer and therefore a significant increase of computing capabilities. In the past, automatic calibration was never done. It was just trial and error. And when I say in the past, I mean until the 80s. And then, again, with the availability of modern computers, people started to perform research on automatic calibration. Automatic means basically that the evaluation of the model performances and the trial and error procedure then is operated by the PC without our direct intervention. We may set up some constraints, like fix the feasible range for model parameters, but then the PC does everything by itself. And there are many and many algorithms that are available in the softwares to perform that. And usually they need to know what are the parameters to be calibrated. They need to know how to measure the model performances. Therefore, they need typically some observed value to compare with to be compared with the model output. And they need to know, and this is most important, they need to know how to make the comparison, which is automatic. Automatic calibration has the very relevant advantage of being done by the PC, which means the possibility of performing many and many trials repeatedly without getting tired and in a short time. Because, you know, if you have to perform many trials by hand, it takes a lot of time. While if this is done by the PC, of course, it's more efficient. There are some problems, and basically the problem is to judge the model performances, because of course we have to define criteria to deliver to the PC for that. But the PC has not the sensibility of a human, and therefore the PC needs, the PC cannot take an overall look to the model performances. He needs, and we will see how to what solution we have, he needs criteria, mathematical criteria to evaluate the performances. And mathematical criteria are always less reliable than the human judgment. This is the first problem. The evaluation is done automatically. The second problem is that, you know, with a trial and error procedure that is performed by you, you get really a clear perception of what's going on, because you try many different parameter values and you see the effect on the output. You get really experienced, and therefore when you apply the model in practice, you are more confident on what comes out. If everything is done by the PC without perceiving what is done, then you get a result, and of course you have always to be in doubt on the correctness of the results and what they mean. So it's important not just to trust the computer blindly. We have many algorithms. We don't go into the details. Even if you look at in R, there are many possible algorithms that can be used. They usually have advantages and limitations. And we don't need to go into the details, because usually today these algorithms are well performing. So I think that a relevant difference is their speed, but usually in the performances they are quite good, and especially for our needs in hydrology, where we have a lot of uncertainty due to other reasons, they usually perform as well. The problem is that we need to define what is called an objective function, meaning the tool that the PC uses to compare model performances and with the observation. So we need to define this objective function, and this is really a relevant issue in hydrology. How to define an objective function? Let me give you some examples. And the most used is the least square objective function, which is minimi quadrati in Italian. Least squares means that usually you are simulating an hydrograph, which is a graph of the river flow with respect to time. And usually you have an observed hydrograph to simulate, let's say this one, and then you get a simulation by PC. And the objective function is something that quantifies how much the simulation is close to the observed data. So least squares is the most used solution, which means that for any observation, you take the difference between the observed value minus the estimated value, then you square the difference and you take the sum over all the observations. This is least squares. Least squares have a relevant limitation. This objective function has many limitations. We will speak on the most important of them. Perhaps the first limitation that is really evident to see is that this sum usually is a huge number, because you take the errors, you square the errors, and you sum over all the observations. So you get a huge number, like billions. And therefore, when you see this number, you don't get a really useful information on the model performances. Of course, the only thing that you know is that you should minimize this number. You should find the parameters values that make this number as small as possible. But just looking at the value of the objective function, you don't see really something useful. And please note that if the model was perfect, then the objective function would be 0. Now, people started to wish to have instead a measure of model performance that is more significant. And therefore, in the 70s, beginning of the 70s, 1970, Nash and Sutcliffe, two famous hydrologists, introduced what is called the Nash-Sutcliffe efficiency, which is this objective function. Let's see how it is computed. And let's, first of all, concentrate on the numerator. The numerator is the sum of squares. So here you have the same quantity then that we had above. Okay, fine. So keep in mind, this is least squares. At the denominator, we have, again, a squared function, which is the difference between any observation and the mean value. And this is fixed. It doesn't depend on the parameters. Because again, these are observations, they don't change, because observed value don't change if you change the model. And their mean value, at the same way, doesn't change. And here you have a number 1. Now, you see that this function, Nash-Sutcliffe efficiency, is equivalent to the least squares, because the only quantity that varies is the sum of squares. So they are similar. They lead to the same solution. So one may wonder, so if they are similar, why did they introduce a different objective function? Because they wanted to reach the target that I was mentioning before. So to get a more informative output from the objective function, let's understand why this objective function is more informative. And to get this perception, let's refer to the case of the perfect model. For the perfect model, I said the least squares are 0. So what is the value of the Nash-Sutcliffe efficiency for a perfect model? Is 1. So the Nash-Sutcliffe efficiency gives a value of 1 to the perfect model, and then this value decreases for decreasing model performances, because of course we have here 1 minus something, and the something is something that increases with decreasing goodness of the model. Okay, so the upper value is 1. Now, fine, but let's see what happens for decreasing model performances. We know that the efficiency decreases. Very often we drop Nash-Sutcliffe and we just say efficiency. The efficiency decreases. And is it possible to get a value of 0 for the efficiency? Yes, of course. You get a value of 0 when the sum of squares is equal to what we have at the denominator. And be careful, this is a very significant situation. Because when you get an error, a measure in this case of the error, given by the model, that has the same value with respect to this quantity at the denominator, we get in a very particular situation. Let me explain why. First of all, let's assume that you didn't have any model available. You have an observed time series, like an hydrograph, and you don't have any model, and people ask you, What is your guess on the next observation? What would you say? You would say the mean value. It's the only information that you can compute if you don't have any model. You may take the average value of the hydrograph and say, okay, my guess is, unless I have more information, my guess is the mean. In fact, the mean is called, in this case, a baseline. Now, this is what you find here. The difference between each observation and the mean value is a measure of the error that you get when your best prediction is the mean. So if you are in a situation in which your best prediction is the mean, you get this measure for the error that you make. Fine. Then, if you use a model and you get the same error, then you would probably better discard the model and make your prediction by just taking the mean. This means that the model is not useful at all. I hope the concept is clear. Let me explain again. If you get a model, you decide to adopt a model, and the model makes, of course, some errors. And these errors are comparable to the errors that you would make if your prediction was just the mean. This means that the model is completely useless. And why to use a model that doesn't allow you to improve your prediction with respect to simply using the mean? It has no meaning. It's better at this point to use the mean. So if you get the same, again, the same measure of error, it means that you get an efficiency of 0, and therefore an efficiency of 0 means that the predictive capabilities of the model are just as much as the mean. So an efficiency of 0 means that your model is useless. On the other hand, if you have an efficiency that is greater than 0, it means that your model improves the prediction, the simple prediction given by the mean value. Is it clear? So and so. So basically, we usually say that from a technical point of view, the feasible values for the efficiency are between 0 and 1. Question, would it be possible for the efficiency to get lower than 0? Yes, it is. Because if you have a model whose performances are worse than those given by the simple predictor given by the mean, and this is possible, it happened to me many times, then you get an efficiency lower than 0, which means that the model is more than useless, is dangerous, is counterproductive. This is possible. If you have a very wrong model, you can get worse performances with respect to just guessing the values by using the mean. Just to give you an information, the Nash efficiency takes a value that is very close to the R square of the regression, of the linear regression. Meaning that if you perform a linear regression of observed versus simulated values, so here you see, instead of depicting the hydrograph in this way, you could depict the hydrograph in this way. Put x hat t here and xt here. In the ideal situation in which you get the perfect model, you have a straight line which is the bisector of the span. If you have any simulated value that is equal to the corresponding observation, you get a straight line. What happens actually is that you don't get a straight line, but you get scattered point. And the closer the scatter to the straight line, the better the performances of the model. And therefore one may say I compute a linear regression of observed versus simulated. You can compute a linear regression. If the linear regression is perfect, then you are happy. And you may know from your background that the goodness of the fit of a linear regression can be measured through the R-square coefficient, what is called in Italian R quadro. And the R-square is very close to the value of the Nash efficiency. Very close. It is defined in a slightly different manner, but the values are very close. Now, a question could be, what is a good value for the Nash efficiency? Because the advantage of using it is that we have a measure of model performances that is more informative. More informative because we can recognize by looking at the number if a model is good or not. While we can't recognize the same information if we look just at some squares. So the relevant question is, okay, but what is a good value for the Nash efficiency for an hydrological model? Of course, it depends on the use of the model, but we usually say that at least we require an efficiency greater than 0.5, at least. Because if the efficiency is lower than 0.5, it means that the model is really poor. But keep in mind that if you want to use the model for technical purposes, meaning you really want to guess an estimate of future values or simulated values, you need an efficiency of at least 0.85, which is not easy to get. Really, it's not easy to get. And I'm talking of performances for rainfall runoff model at daily or hourly time scale. If you work at monthly time scale, then you can get better performances. If you work at daily or hourly time scale, it's difficult to get good performances because, you know, it's very detailed description. So in these cases, if you get to 0.85 is good. The model can be used for technical purposes. If the efficiency is 0.6, you know, you may still use the models for research, but for technical purposes, it's not really good.